So we've just finished looking at the alkanes, the alkenes, the alkynes, and then their structural isomers, ways in which we take long chains of fairly useless hydrocarbons and break them down into shorter, more branched, more useful hydrocarbons. But the one thing that the three homologous series have in common is that they were all chains. Okay, if you think of all the alkane molecules, all the alkene molecules, and all the alkyne molecules that you've just met, they're all long chains. And we count the longest chain, and then we counted the branches on the longest chain, and that was our way of naming them by the IUPAC rules. There is one other group of hydrocarbons that we haven't spoken about yet, and they are the hydrocarbons that contain, if you take a look at this slide here, these most unusual structures. That structure there is the old-fashioned way to describe a molecule of benzene. Okay, now benzene is a most unusual molecule because of its properties. On its own, it's extremely toxic. In fact, on its own, it's carcinogenic. But when you start to attach things to benzene, you get hundreds and hundreds of very, very useful products. Whenever benzene is involved in any molecule, the molecule is classified as being aromatic. Now, we're probably familiar with the word aroma, smell. So things like the peel of a lemon, the peel of a grape, things like the smell of almonds, the smell of marzipan. That's all based on benzene. So therefore, yes, things that have a nice scent could be based on benzene. Okay, but anything that contains benzene must be described as aromatic. So therefore, what name do we give to the long chains that we've just finished looking at? The alkanes, the alkenes, and the alkynes, and all their isomers. They are in the opposite group to the aromatics, which are called aliphatics. So there's only two ways to break down all your hydrocarbons: those that contain benzene, the aromatics, and those that don't contain benzene but have long chains, and they are your aliphatics. Okay, so therefore, if we're asking ourselves a question, if you look at a molecule and you ask, is this an aliphatic compound, is this an aromatic compound, all you have to do is look for the presence of benzene. But what does benzene look like? Okay, and where did it get its structure from? We'll look at that in a moment. Aliphatic compounds contain carbon chains, as we've already said. Something like that, for example, which you can name yourself. 1, 2, 3, 4, 5. There are 6 carbons, all single bonds, no branches. So that's just basic hexane. Okay, so hexane would be an aliphatic compound, and that's the way in which we write it. Normally, in a lot of the scientific journals, that's the proper way to write hexane. But in order to show the addition of hydrogens as well, that would be in the beginning. This is what we would look at in terms of being hexane. Aromatic compounds, we said, are based on the benzene ring. Now that's the structure of the benzene ring. Okay, it's very much like a nut that goes over a long screw. That's exactly what it's like. Something you've got to use a wrench with to try and tighten or loosen or whatever. It's exactly the same diagram as that. But we're wondering, where did it get its diagram from? Where did this come from? Well, in the beginning, when they were trying to decipher the structure of benzene, they realized that benzene, in order to be the molecule it is, had to contain alternating double and single bonds. So in other words, when they tried to draw this the first time, what they came up with was something like this. So they had a molecule where they had alternating double or single bonds. And then somebody very smartly said, well, hold on a second, this is just as good. Maybe it's this way. And all they did was they put the double bonds on different carbons. So this is carbon number 1, 2, 3, 4, 5, and 6. And this is carbon number 1, 2, 3, 4, 5, and 6. You can see very quickly that there are actually two possible structures that are isomers of each other. Okay, but benzene can't be both at the same time. So therefore, they had to come up with a way of deciphering how they would get a proper structure for benzene. And it wasn't until X-ray crystallography came along that they were actually able to decipher what the structure of benzene is. Okay, they discovered that first and foremost it's a 6-carbon ring structure. But instead of having what we said a moment ago, alternating double and single bonds like that, what they discovered was that it was a hybrid. Now let me explain that to you. If a molecule was to have alternating double and single bonds, think about double and single bond. A double bond has 4 electrons, a single bond only has 2 electrons. So therefore a double bond is more electron rich, and it will be a shorter bond. Okay, because there's more electrons involved holding the atoms together, it'll be a shorter bond. So what they expected to see was short, long, short, long, short, and long. So even though it was a hexagon, they were expecting to see alternating lengths, which would distort the shape somewhat. When they took an X-ray of it, the crystals of benzene, they actually discovered that it wasn't a situation where they were short, long, but all of them were in between. It was the average, or what we call in science a hybrid, a kind of a mix between the two. So instead of having long, short, they had average, and average. So therefore we ended up getting a molecule where we couldn't actually write down the double bonds. So what we did was this. We kind of said, okay, there's an average, and average. Do you see where the circles beginning to come in? Okay, now how did this hexagon inside turn into a circle? Well, on further inspection, they discovered the following, that benzene has carbons here, okay? There's 6 carbons. Now, each of those carbons spend one bond holding one neighbour and another bond holding another neighbour. They then also attach on a hydrogen to themselves, like that, which now means that each carbon is using up 3 bonds. But if you go to the periodic table, you'll discover very quickly the carbon has the possibility of making 4 bonds because it's in group 4, which means that there was an electron left over here, an electron left over here, an electron there, an electron there, there, and there. That actually wasn't involved in bonding at all. So what these electrons did was they left the carbon that they were with, they went into a shared area, and they began to spin around in a circle. And they spun so very, very quickly above and below this hexagonal ring structure of 6 carbons that it pulled the carbons together into a very, very stable molecule, which we now know as modern day benzene. Okay, so that's where that came from, that particular diagram. So, one electron, as we said already, from each carbon is delocalized. Now think about it again. Take just one carbon. That carbon holds on to that neighbour, and it holds on to that neighbour, and it holds on to a hydrogen. So therefore there's one electron left over that's not involved in bonding. And that is delocalized. That's what that means, delocalized. It means that it moves away from the carbon that it belongs to into a shared area, and it begins to spin. And in fact, it's shared over all the carbons. So there will be 6 delocalized electrons rotating around this hexagonal ring, forming a bunch of delocalized electrons which bind the molecule together into something that's extremely stable and extremely unreactive. Okay, so therefore the 6 delocalized electrons, as we said, they rotate about the whole molecule, strengthening it, stabling it, and making it highly unreactive, and we get what's called benzene. And that's where that shape comes from. So if I was to do this, you'd see exactly what that means. There's the electrons rotating. So think about it. Carbon, 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 and carbon. That carbon here holds onto that one, holds onto that, holds onto that, that holds onto that, that holds onto that, that there. There will be a hydrogen as well on each one, like this. So we've got a bond there, 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 and there, and there, which means there's one electron, as we showed you already, on the edge of each of these that basically enter into this delocalized area and begin to spin. And as they spin, they pull it together, pull all the carbons together into a very, very stable molecule. Okay. So, the circle in this new diagram is the new structure, and that's the structure now that we use for benzene. So gone is the diagram we already had, this diagram here. You may see it sometimes, but it's the old way of representing benzene. Benzene is not represented like that. That is not allowed. So the new structure for dealing with benzene is a hexagonal ring with a circle in the middle representing the what we call delocalized electrons. Benzene, as we said, is carcinogenic. Very, very dangerous, okay? Dangerous to human health. But because of these 6 delocalized electrons that are spinning and pulling the carbons in and strengthening and stabilizing that molecule, it also becomes very unreactive. So it takes a lot of effort to get benzene to react with anything. However, when we do get benzene to react, the number of compounds that we make on the backbone of benzene are remarkable. We've got things like limonene, which is in lemon peel and orange peel. We've got things like codeine, which is a medication for the relief of pain. We've got things like heroin, like cocaine. They're all based on the benzene ring. Caffeine, they're all based on benzene ring. We'll study benzene in more detail later on when we come back to the hydrocarbons again, particularly the aromatic hydrocarbons. Methyl benzene is a very, very safe substitute. Now, what have I done there? Look at the two names. What was benzene is now methyl benzene. So say, for example, you were asked to draw methyl benzene. What would you do? Well, first of all, you would draw benzene, and you draw it the way in which we draw today. You would draw benzene like this, the circle of delocalized electrons, and then on any of the carbons, it doesn't matter, because if you're only putting on one methyl group, all those carbons are going to be number 1. There's no way to know where we're going to start and end. So therefore, to do this, C, that is methyl benzene. And what happens is, even the addition of a methyl group removes the carcinogenic nature and makes it a very, very safe substitute to work with. And in fact, it's so safe, we have this methyl benzene in the lab. We're allowed to have it. We are not allowed to have benzene, but we are allowed to have methyl benzene. And it's the difference between the CH3 being attached to the benzene ring that somehow tames the molecule from being something very carcinogenic into something that is quite less dangerous. Okay, there it is there. And then we have, of course, if we go up another one, ethyl benzene. And ethyl benzene would be simply the benzene ring with 2 carbons attached to the ring itself, something similar to that. So you know how to name these things. All 3 are organic solvents. Now, normally, why do we need organic solvents? Well, nearly everything dissolves in water, but there are certain things that don't dissolve in water. And any time we have a substance that we simply can't dissolve in water, we call in methyl benzene, and methyl benzene will dissolve with no problem. So when we talk about an organic solvent, we're talking about a liquid that will dissolve things that simply don't dissolve in water. Now, I know water is called a universal solvent, which means nearly everything dissolves in it, but those little things that don't dissolve, like for example bromine won't dissolve in water, iodine won't dissolve in water, but they will certainly dissolve in the organic solvents like cyclohexane, or like for indeed methyl benzene or ethyl benzene. So let's talk about cyclohexane. I mentioned it a moment ago. This is another organic solvent, okay? And cyclohexane as an organic solvent is what we use on substances that don't dissolve in water, like benzene. Now, the unusual thing is that there are 6 carbons in a ring. So in other words, cyclohexane looks like this. But that's all. Notice what's missing? There's no circle in the middle. This is not benzene. Therefore, this is not aromatic. And if it's not aromatic, it must be aliphatic. It has to be, okay? Because that's cyclohexane. And cyclohexane is nothing more than hexane, which is 1, 2, 3, 4, 5, 6. If I was to draw the whole thing, that's the way it would look. They're all hydrogens, okay? And I remove the terminal hydrogens. So in fact, I remove this hydrogen here. Oops. I remove this hydrogen here, like that. And I remove this hydrogen. And then all I do is I tie the 2 terminal carbons end to end, and that becomes like this. And that is cyclohexane. It is not benzene, it is not aromatic, it is still aliphatic, for the very simple reason that benzene isn't present. Something can only be aromatic if benzene is present. Okay, so is a hexane chain, cyclohexane is a hexane chain that has been linked end to end. So as I told you already, you remove the 2 terminal hydrogens and then you connect the terminal carbons to one another and a hexagon forms, but it's not benzene, it's cyclohexane, and it's still, as we said already, an aliphatic compound. It is not an aromatic compound. It's an aliphatic molecule that is simply linked up end to end. And that's a better representation of cyclohexane there. Now, do you notice anything? Cyclohexane, CnH2n plus 2 is the normal general formula for an alkane. But here, if we notice, C6H12, there seems to be 2 hydrogens missing. Remember what I told you? We cut off the 2 terminal hydrogens from the chain of hexane, and then we connect the terminal carbons end to end. So that's why there's 2 less hydrogens in this hexane molecule than there would be in a long chained hexane molecule. This one here, give a guess. Again, 1, 2, 3, 4, 5, 6. So it's hex something. Is it benzene? No. So it's not aromatic. This is still aliphatic. If it was benzene, there'd be a circle in the middle. All right. So what's this one then? Well, it's hex, and it has a double bond. So it has to be ene. But who's carbon number 1? We simply don't know. Where do we start counting? We've no idea. So therefore, what we simply say is, well, wherever the double bond starts, that's carbon number 1. So this is simply hexene. Okay. And because it's in a ring, cyclohexene. Okay, that's where the name comes from. So, cyclohexene is again an aliphatic molecule. It is a hexene chain that has been joined end to end. So again, the terminal carbons or terminal hydrogens are removed and the terminal carbons are linked end to end. They form a hexagon, but the hexagon now contains the double bond that was in the original hexene molecule. It's not benzene, so therefore it is cyclohexene. Okay. I just want to move on to fractional distillation just to finish this little section. So the lesson today is not that long. But fractional distillation, by its very name, we all understand what distillation is. Distillation is the way in which we boil a liquid, turn it into a gas, then send the hot gas into a cold area like a condenser, where it is then condensed back to a liquid and collected. Now we normally do that as a way of purification. So therefore, when we were in first year and we were talking about distillation, we were saying you could use distillation to separate water from salt. You can also use distillation to separate alcohol from water. So if you mix alcohol and water together and you put them into a distillation apparatus, the alcohol will boil at 78 degrees and it will come down the condenser first. And then the water will boil at 100 degrees and it will come down the condenser second. So distillation is a lovely way to separate liquids and gases and solids that have different boiling points. And that's extremely important to what I'm going to talk about now. All right. So what's fractional? Well, fractional just means pieces. So therefore, here we're going to use the process of distillation to break something up into fractions, to break something up into pieces. What are we going to break up into pieces? And the answer is this thick, black, smelly liquid that you see up here, which we call crude oil. Okay. Now, why is crude oil of such huge value? The answer is the oil itself isn't of any value. When they go down to the ground, when they hit oil, and when the oil comes out of the ground as this big, thick, black, smelly liquid, the liquid itself is of absolutely no use. If you try to burn this thing, it won't burn. All right. But what the black liquid has inside it is a mixture of extremely useful hydrocarbons. So the first thing I want you to know about crude oil is that crude oil is a mixture. And it is a mixture of very useful hydrocarbons. Now you can see where fractional distillation is going to come in. So what's in here? Well, things like methane, ethane, propane, butane. Things like ethene, things like propene, things like hexene, things like petrol, things like naphtha, things like diesel, kerosene, you name it. All the important fuels that the world has such a demand for are present in this thick, black, smelly liquid. But the thick, black, smelly liquid itself of absolutely no use. So what we have to do is we have to take this black mixture, we've got to put it through the distillation process so that the distillation process will break it up into different pieces. And that's the most important thing. Okay, I'm going to break it up into different pieces. So how do we do that? Well, let's take a look. Crude oil, as we said, in its raw state is of very little use. It is a mixture of many useful hydrocarbons. The useful compounds are separated in fractional distillation. Now keep that in mind. What's distillation? It's bringing something that is a mixture up to the gaseous state where it can be taken away and condensed. And the reason why it's separated is because the substances that we're heating all have different boiling points. Okay, and just to show you what that looks like, this is what we call the fractional distillation column. Okay, so this is the fractional distillation column. And it's a huge big apparatus. It's not a small little thing that just fit in your back garden. This is a big industrial thing, okay? And what happens is this. The crude oil that comes directly from the ground is heated here, heated on the way in by burners. And everything here, almost 99% of everything that comes in from crude oil is immediately vaporized. So it's so hot that it's vaporized. And all the gases then enter this fractional distillation column. But what happens is, as the gases begin to flow through, they begin to drop in temperature. So therefore they come through here like this, up in there, and then they come up like this, up through this fractional distillation column, like so. But as they reach higher and higher and higher in the column, the temperature of the column begins to drop. And when they fall below their boiling point, they will fall out as a liquid. And where will they fall out onto? They'll fall out onto the trays here. And then they will be carried away as one fraction. So therefore, the smallest hydrocarbons, the ones that are of most use, they're going to make it right to the top. They're going to make it up this way, here, and then make it right to the top and away. Things like what? Things like CH4, yeah? Things like methane, things like ethane, propane, butane, camping gas, all that kind of stuff. They're the smallest molecules, and they're going to find their way right to the very top and be pumped off from the top as gases. They stay as gas, okay? Then, as we move down, we get petrol. So the next heaviest fraction would be petrol. There's a massive demand worldwide for petrol at the moment. So therefore petrol is extremely useful and therefore has a very good high price on its head. Then we get naphtha, and naphtha is the gateway to the petrochemical industry. All right, and we'll talk more about that later on. But this is the petrochemical industry. And this is where we get our plastics from and so on. Okay, so that's a huge, well, I suppose an expensive thing. It's a thing of huge importance. Then next heaviest is kerosene. Now kerosene is quite a block of a chunk of hydrocarbons, and it is used as a fuel in the bigger engines. So things like, for example, jet engines that do these long haul flights, they would use kerosene as their fuel because they burn it, it's efficient as a fuel, but it delivers quite an amount of energy per gram, so it lasts. And that's the reason why we now have planes that can fly from London directly to Australia without going for a break, okay, thanks to kerosene. The next heaviest one then would be diesel oil, so we're getting really heavy fractions at this stage, which would be used in buses and so on. And then at the very end, there's only one fraction that doesn't vaporize, and what it does is it trickles out down here as a very thick black sludge, and that thick black sludge that comes out here at the bottom is what we call tar. It's on the surface of the roads. So that black stuff you see them putting on the surface of the roads, that's the heaviest fraction that comes out of the fractional distillation column. That's of practically no further use than lining our roads and giving them a surface that's resistant to wear and tear. It lasts quite a long time. It's almost like plastic. Yeah, it's that thick. So listen to it again. What happens? Let's just go through it again very quickly. The crude oil enters from the bottom. The crude oil is heated by burners. Okay, it vaporizes. 99% of the crude oil vaporizes. The only one that doesn't vaporize, as we said already, is tar. Okay, which they call bitumen. There it is there, bitumen for road surfaces. Okay, or tar. All the rest vaporize, and the ones that have the smallest length are the ones that have the lowest boiling point, and they will go right to the top. So things like methane, ethane, propane, and so on. And then as the chains get longer, the boiling point goes up. Okay, so next we've got petrol, then next longest will be naphtha, kerosene, diesel oil, and so on. Now these fractions, you do have to know them. You have to know what the material is that comes out at a certain fraction, but not only that, you have to know its use, you have to know its chain length, and you also have to know the temperature at which it condenses. All right. Now I have summed all of this up on the next slide. And by the way, there's a little link down here, which when you get the slides, click on that link and have a look. All right. It'll actually show you this particular process in action. It'll show you the little tiny chains shooting up the top and the long ones then falling down the bottom and being tapped off as sludge. And then the ones that are of medium length fall off in the middle, the ones that are longer fall off towards the bottom, and the ones that are shorter towards the top. So do click on that link down here, have a look at this in action and see if you can work out where your fractions are. It's a nice way to help you to remember where the different fractions are. So what have you got to remember? What am I going to leave you with? I'm going to leave you with the following table, and that is something that you have to learn. Okay, so what we have at the very top are our refinery gases. Next biggest, petrol, naphtha, kerosene, diesel oil, lubricating oil, fuel oil, and then bitumen, which is the biggest molecule, doesn't vaporize, comes off the bottom as a big thick black sludge, which we throw onto the surface of the roads and allow the cars to drive over it for numerous years. It's quite resistant to wear and tear. The boiling points, as you'll notice, the longer the chain gets, the higher the boiling point. Yeah, so here's your chain from C1 to C4, boiling point of about 25 degrees. When you get up to a chain of bitumen, which is tar, you've got more than 35 carbons, which gives it a boiling point of over 500 degrees. All right. So the difference between 4 carbons and 35 carbons is the difference between boiling at 25 degrees Celsius and 500 degrees Celsius, which is quite something when you think that these are only atoms of carbon that you're adding on. What do we use them for? Refinery gases are used for bottle gases. So if you own a mobile home, or if you went on holidays where you had to have camping gas, you have these little canisters of camping gas that contain more than likely butane and probably propane. And they're the fuels that we use, portable fuels. Then you have petrol, which is a motor fuel. You've got naphtha, which is, as I said, the gateway to the petrochemical industry. That's extremely important. I'm going to mark that out. That's very, very important, because that's where we get our medicines from, our plastics, our detergents, and our solvents. Okay, so there's a massive industry on naphtha alone. That's why it's so expensive. Then we've got kerosene, which is a fuel used for maybe airplanes. Diesel oil, which is heavier than diesel itself now. Diesel oil is a heavier fraction than diesel, and that's used in trucks and buses and so on, the big heavy engines. Lubricating oil, you put it onto the chain of your bicycle, you put it into machines that are constantly in motion so that it reduces friction. Then you've got fuel oil, which is for the big cargo ships that go between, at the moment, say the US and Ireland, or the US and China, or wherever they're going to go. But these are big things, okay? And I suppose aircraft carriers as well. The big ships, they would use fuel oil as their particular way of motoring the ship. And lastly, then we've got bitumen, better known as tar, which is used simply for road surfaces. So I'm going to leave you with that, and I want you to learn that table. I'll give you some questions to do in relation to this particular table at a later date, but learn those fractions, know how the distillation column works, go back a slide, click on the live link, it'll give you a little game that you can play, it'll give you all the fractions at the bottom, and you have to arrange them at the various different heights, and it'll only let you finish the game when you get all the fractions correct. So it's a nice little way to help you to try and remember them. And again, if you need any further clarification, send me an email or give me a shout.